present as well as the input condition. Okay, present state and the input condition. So in this section, basically we'll see what are the different logic circuitries are there related to the sequential design, especially related with the latch and flip-flop. So you can see, we'll discuss this particular topic. What is the basic memory cell for a sequential design, how it works, then how it can be used as a SR latch or GK latch or D latch or flip-flop and clock CMOS logics. So the first, you know that there are two type of logic circuitries: combinational logic and sequential logic. Okay, and the sequential logics can be again categorized in the three based on the stability. Okay, there is a bistable, monostable, and astable. These three category of there, because it is called the regenerative circuits, and they are why it's called regenerative, because there is a feedback mechanism is there. So in combinational circuit, we don't have any feedback mechanism. So so the bistable circuits, what do you mean by bistable? So bistable circuits means, is from the name you can interpret by yourself, that bistable circuits have two stable operating points and will remain either in state unless uh, it is changed from the input. Like if you want to switch, like CMOS inverter has two stage, either logic 0 or logic 1, and both are at the stable state. Okay, and by providing suitable input, we can change the uh, state. Okay, so memory latches in also the information are stored in form of a logic 0 or logic 1. Okay, and then for that we required which kind of sequential element? We required a memory cell, or memory cell like DRAM or SRAM kind of memory cells are required, or latches we required. We can have a like some storing information in terms of latches, flip-flops, and registers. Okay, this all comes under the sequential circuits. So what is monostable state? So monostable circuits have only one stable operating point, and even they are temporary perturbed to the opposite state, they will remain, they will return in time to their stable operating point. Okay, so only one stable state is there, either 0 or 1. Okay, based on the designing of the circuit. And you know that and the last one, astable circuit. So astable circuits has no stable operating points and oscillate between the several state. So example of a this kind of astable circuit is a ring oscillator. So where in ring oscillator, it is continuously oscillating over the period of time. So basic bistable, we in case of a generally sequential circuit, we choose a good bistable circuit. Okay, so this is the example of a simple small one memory element, that is a bistable circuit. Okay, and how that can be stability can be defined. So is you can have a two inverter back to back connected. Okay, one inverter output is connected to the input of another inverter, in similar fashion other one also. So if you want to make a CMOS diagram, so this is the CMOS diagram you can see. Okay, inverter back to back connected, V output 1 is connected to V input 2, and V output 2 is connected to V output 1. So this is a gate based representation, and this is a CMOS based representation. Okay, so how it will have a bistable nature? So for that we need to draw a VTC curve, that is called the voltage transfer characteristics of a CMOS inverter. If you know that, then it is a V input versus V output. So if V input 1 is there, V output 1 in the Y axis will be there, and this will be the characteristics like this. When input is 0, output is 1, and then it is going like this, and when input is high, output is 0. Okay, then similarly, because there are two inverters and another inverter is flipped one, so what will happen? The one output will be this. This will become V output 2. Okay, and this will become V input 2. Okay, so if you draw this, flip the axis, and x become y and y become x, and both the things in one graph. So it will show like this. It will seems like a butterfly. It is called the butterfly curve. Okay. So you can see this the two uh, closed loops, you can say two closed loops are making the butterfly curve. Okay. And if you note down in terms of energy, and in case of a CMOS also, we have seen that the power dissipation is maximum at this particular center when all the transistors are working, or you can say short circuit power dissipation when both NMOS and PMOS are on. Okay, at this is the particular point when both the transistors are, in this case you can say all the four transistors will remain on, where the energy consumption will be high, and then it is a unstable state. Okay, because this state is not defined, it is a logic 0 or logic 1. So the what are the stable states? That has to be uh, uh, completely good VDD or completely lower value, so that will be defined as the completely stable state. Okay, so in terms of noise margin analysis, basically we also find out the VOH and VOL. Okay, as I told that you should read about the noise margin. So what is VOH and VOL? Is basically VOH is called the voltage high, and VOL is called the output low. So what is output high maximum possible, and what is and because of the noise and all. Okay, and it is going into the second stage, so it may disturb the information. Okay, so we output like if we, this is a parallel arrangement. If we have a series arrangement, what will happen if the series arrangement is there? So suppose this is a series arrangement, so this output of the first one is connected to the input of the second one. Okay, so in between there may be possibility that there is a noise has been introduced at this particular input point or at this particular point, or you can say both the nodes are same. So if this particular node, if any small connections or environmental issues are there, okay, because of the environment, these are connected to metal lines. Okay, some noise are introduced, some spikes are introduced, so that will change the information. So if it is suppose it VDD, and if it is changed by a small value, okay, so that is why the name in noise margin has been four different parameters. One is called VOH, and one is called the VOL points. Okay, so output low points will be at this particular stage. So VOH can be now VIH for this particular point. Okay, and this become VIH, then the output will be VOL, output low, because this is high input. Okay, and then if it is a high input, so sorry, low input, so now it is going to the next stage. Again it is disturbed, so it may be disturbed at this particular point, right? So that will consider as another point, that is called the VOL. Okay, sorry, VIL, input low. Okay, so that these four parameters are decide the noise margin of the device. And in general, if you talk about the memory application, so this butterfly curve also can be used for estimation of a noise margin. So what is that? The thing is that we need to put a square box. Okay, if you put a how much size of square I can fit inside the butterfly curve decide the noise margin of the particular memory element. Okay, and if you don't know about the VIH, VOL, all those things. So one method is by calculating the VIH, VOL, all those things, all four parameters. You might have gone through the book. Okay, and second method, as I told, using the butterfly technique. So inside the butterfly curve, put the square box, maximum size square box possible, and in the square, you know that one edge is similar in all the edges. Okay, so if you measure the particular one edge, suppose this in terms of voltage is there one, and this is the 5 volt maximum voltage, so maybe the edges will come to the around 1 volt. So 1 volt will be the noise margin of the particular memory element. Okay, so this way we can derive the noise margin of the device using the butterfly technique. Okay, so in actual physical circuits, the memory cell will never stay in unstable point. Okay, since any small electrical noise in the circuit will trigger to one side or other side. Okay, so because that is why noise margin is an important factor. If the noise margin is very high, okay, so in that case we'll get the no disturbance. Okay, so that is why it is said that the noise margin value should be very high. Okay, and if you ask you a simple question, what should be the noise margin of a simple inverter, ideal inverter? Can you guess the answer? What should be the noise margin for the ideal inverter? Any idea? ठीक है, so what is the ideal characteristics? अगर हम ideal characteristics की बात करेंगे, how it will make a ideal characteristics. तो CMOS के लिए ideal characteristics ये होता है, this is the ideal characteristics of a CMOS. Okay, and this is the practical one. ऐसे अगर कर देंगे, this is practical one. So you know that in ideal characteristics is like this. So what will this particular point, this straight line that is going down, that is equal to VDD. Okay, so we can say VDD by 2. So in ideal any ideal CMOS, the maximum noise margin possible, that is equal to VDD by 2. Okay, and in practical situation, if we measure this the square box inside the butterfly curve, that will always be less than VDD by 2. Okay, suppose VDD is 3 volt, so always noise margin is less than that. Okay, it depends upon the measurement. Okay, and for the ideal value, it should be equal to VDD by 2. So in SRAM cell, basically, if you are using this as a memory, okay, you can make a SRAM out of it. So you know that our which kind of memory is the fastest one? The SRAM that used in along with, and we always talk about the memory application, 6 GB RAM, 8 GB RAM, all those things, right? This is, we are talking about SRAM only. So SRAM is one SRAM, how the information can be stored. The basic building block behind the SRAM is this block only, this block only. Okay. So now we'll go to the talking about the SR latch. Okay, so SR latch can be prepared by two ways. One is by using the NAND gate functionality and NOR gate functionality, because you know that NAR and NOR both are considered to be a universal logic gate. Okay, so that is why both the functionality is possible. So you can say, if you have a in terms of logic unit, in terms of gate, this is the diagram where S and R are the input and output are equal to Q and Q bar. Okay, this is the conventional SR latch you might have studied in your earlier classes. Okay, have you studied this thing in earlier classes, SR latch?
Yes, sir.
Yes, sir.
Okay, yeah, so the only thing is that you, if you have already studied, then you also be knowing about the truth table. Okay, SR-less truth table. This is the SR-less truth table, and one is Q n plus one and Q n plus one bar. Okay, so it will depends on the previous state. Okay, so yeah, the operation is like SR-less. In summary, we can say if the both the inputs are zero, it is in the whole state. If S is one, that is called the set operation. If R is one, that is called the reset operation, and if it is one is there, that is called a not allowed state. So only three states are possible. Okay, so only here I am going to tell you, that is only thing that I am going to tell here is that you should able to make a the circuit of SR lathe using the CMOS technique. Okay, so if you want to make a this particular diagram using the CMOS, how we can make it? 1 minute, sir. I am class. Okay, so you can see that how they can be built. Okay, just see this diagram and you will be able to write, because it is a NOR gate. Is two NOR gates are there. This is one NOR gate and this is another NOR gate. So just prepare two NOR gate. So while preparing one NOR gate, how many number of transistors are required? Using static
Four.
CMOS logic, 4, right? 2 NMOS and 2 PMOS. So nothing but this is a one NOR gate, two in parallel, and this is in series. Again, this is another NOR gate, two in parallel, two in series. Okay, and then rest of the connections. Okay, suppose this is the output is connected to input, second input. So see which is the output point, q bar. This is the output point and this is connected to input of the another one, this particular point, you can say. So similarly here, this is the output and connected to another input. So we have flipped the transistor. This particular transistor are made in flipped condition so that the connection will become easier. Okay, so you can say and what are the another two inputs? One input is S and R. So similarly, this is NMOS and PMOS are connected to one point that will give one input, and this is another input, right? Okay, so and this is the second input for this, and here also this will be the second input, right? This one. So similarly, the same operation will take place. Only I am talking in terms of CMOS. Okay. So similarly, if we have like if you want to make it using the NAND gate version, okay, similar NAND gate version. So what is the difference between NOR gate version of SR latch and NAND gate version of SR latch? Anybody idea that the circuit diagram is changed now? Okay, so what we have to do? First check this whether the truth table is same or it is changed.
It is changed.
Yeah, correct. It is changed because earlier the S is one equal by used to set. Now S1 is equal to reset, and R1 is reset. Here it is a set operation. The you can say the operation depends on the input condition. Okay, so it is whether it is a NOR or NAND. Okay, you need to verify by yourself. Okay, so we generally go for NOR version so that our concept will be based on the NOR function, where S used for the set and R for reset. Okay, but here when you go for a NAND operation, the truth table will change. Here earlier when not allowed state was 1 1, here not allowed state is 0 0. Okay, so you can just prepare NAND gate similar to previous one, again one NAND gate, and then make the interconnections. So how many transistors will be required to make a SR latch?
8.
8 transistors, correct. So I'm not going into the details, okay, so that you can build any kind of CMOS circuit if you know the logic gates. And you have to also remember that the universal gate, which technique are going to use. Either you are going for 1 minute, please. Okay, so earlier we have used for discussion about the SR latch without clock. Okay, now if you want to make a clocked SR latch, so what we have to do? We need to introduce some AND gate to make a clocked SR latch. Okay, so that you can know this operation and all, right? If when clock is working, high, then only the output will respond according to the value of R and S. These are the two inputs. Okay, so this is the example given, right? So you can say at this particular point, if clock is high and the value of S is high and this R is low, so what should be the output? This is called set, because it is a NOR based operation. So we can say set, that means output has become equal to 1. Okay, so in this way you can make a timing diagram out of it. Okay, and then clock NOR gate, you can say there is an AND gate involved in that. So how to make a AND gate using the CMOS? Okay, so for that we need to introduce some of the more number of transistors. As you know that for building this much of particular block, how much transistors were required? 8 transistors were required. Now the transistor count will increase, right? So this is the implementation of this particular block. Okay, clocked SR latch. So in the clocked SR latch, so there is an AND gate also involved. Okay, so instead of making a NAND gate and then in making invert, that will take more number of transistors. Okay, so instead of using that, you can uh, have another method. Okay, where we can be it can be utilized, like you can see this how they have built basically. So earlier we are two inputs. Okay, so now we can say we have three inputs kind of thing. Okay, where R and clock are connected to one circuit, this particular circuit, they are connected, and another one was connected here. Okay, so R and clock are introduced here. Here also another we need to add. Okay, so if we are adding here also, then we need to add as if one PMOS here. Okay, so you can see that if you are building from this particular logic, whether you are able to achieve the things or not. Okay, so here how many additional transistors have been used for making the complete circuit? You can see count here.
Four.
Four additional transistors are used, right? So that is called the CMOS AOI implementation. That is called AND or invert. Okay, so AND or invert, you know that series parallel combination. AND means what, or means what. In series parallel communication, invert means what. So whenever it is required, you need to put additional transistors for the invert logic. Okay, so if it is already inverted, then we need not to put a CMOS inverter. Okay, so you can see here that this particular circuit can be used as a clocked CMOS SR latch implementation, that is called AOI implementation. So that is called AND. So we can say this is AND and this is OR. Okay, and then we make the fashion, always will get the complementary information. Okay, so that is why it is called invert. So AOI implementation will give you can say this is the optimized one, right? So if you are preparing by your own conventional method, then it may take how many number of transistors? Six alone, and then four. So it will increase the number of transistors. Okay, so better to make it an optimized way by AND or invert logic, so that the number of transistors can be reduced and giving the same functionality for the implementation. So here we can say R and clock are AND operations. This is R and clock are in the AND operation, and after ending operation, they are they are basically in parallel configuration. In how we implement NAND gate in parallel configurations. So this is one input X and this is another input Y. They should be in parallel while implementing the NOR gate. Okay, so this way you can reduce. Similarly, this is X and Y. So in the parallel combination, we can say this is X and this is Y, and this is X and this is Y, right? Right, because this, if X and Y is parallel, then X and Y should be in series in PMOS configuration. So X containing 2 series transistor, here X containing 2 parallel transistors. Okay, so similarly, you can make with the reduced number of transistors, making a clocked CMOS SR latch implementations. Okay. And now, if we go for a, you know that what is the disadvantage of using the SR latch? You have just seen that one condition 0 0 or in case of a NOR gate, 1 1 condition is invalid state. Okay, so how to remove the invalid state? Okay, by using the JK flip flop or JK latch condition. Okay, so for the, you can see this is the JK latch arrangement. That is a NAND version here. It is shown. Okay, not the NOR version. Please note that this is a NAND version of a JK latch implementation where the clocked one has been used. Okay, so instead of a, earlier we had a 2 input, now it has become a 3 input because there is one more feedback has been used from the output side. Okay, so this is the total operations of a JK latch, how it will operate, where this is the truth table in all, right? So what should be the output when JK both are 0? So that is called the hold state. Okay, when JK are both are 1, that is called a reset state. When 1 and 0, that is called the set state. And if it is a 1 1, so instead of an invalid state, it will be a toggle state. So either if earlier Qn will be 1, then the Qn plus 1 will be shifted to 0. Okay, so we can say this is a toggle state. So you know all those things. Okay, so you how to realize the circuit. So basically, so for realizing the circuit, same you can utilize the AND or implement logic. Okay, and you can design the JK flip flop. Okay, and you know that if you have it remove, if you want to use avoid this toggle state, then what we need to use, we need to go for a master slave arrangement. Okay, so this is called master and this is called slave statement arrangement, so that the toggle state can also be improved. Okay, so I'm not going into the details of that. You only study about the circuit part. Okay. Now another simple implementation is CMOS D-latch implementation. Okay. So what is the CMOS D-latch? So D-latch is the simplest is compared to the JK latch, right? You know that if the inputs are J and K are combined together, then we can make a D-latch. Okay, so in the D-latch implementation, there will be 2 ways of implementing, right? One is using the CMOS, okay, and one is using the another thing is called the transmission gate logic. This is called the transmission gate. Okay, this is equivalent to pass transistor also, you can say. So the difference between the transmission gate and the pass transistor is that in the pass transistor we are using only one transistor to pass the information. Yes or no? If it is an X input is there, it will become a Y equal to X if we apply a VDD here, right? So, but there is a problem with this pass transistor. What was the problem with the pass transistor devices? What was the problem with the pass transistor devices? Any idea?
So for NMOS logic, we did not get full VDD at the output. We used to get VDD minus VTH.
Yes, yes. So that is why we are going for a CMOS logic. Okay, but CMOS logic will always give invert function, right? Okay, so that is also limitation of a CMOS. Okay, so if we cannot max, you cannot make a value Y equal to X. It will be only possible if we have a 2 inverter. Okay, okay, so if it is a X, it will become X only after putting 2 inverter. In between it will give X bar. Okay, so to resolve the problem, okay, there is a use of transmission gate. Okay, that will reduce the number of transistors. So if we are implementing using this, how many transistors required? 1. But there is a problem here. Okay, but if you implement them with the same logic CMOS, we require how many transistors? We will be requiring 4 number of transistors. Okay. So is there any way out to design the functionality y equal to x, okay, equivalent to pass transistor? That is called this one. This is called a transmission gate logic. Or transmission gate logic, nothing but whatever information is coming here, let's say it is coming information D here, so it will pass information D, okay, based on the gates input. So like the working is almost similar to pass transistor. The only difference will be there that will get the correct logic. Suppose in case of a pass transistor, we will get VDD minus VTH maximum output in case of NMOS, and in case of a PMOS, we will get the maximum information is equal to VTP. But in case of a transmission gate logic, since you can see in transmission gate, NMOS and PMOS both are connected in parallel. Okay, both are connected in parallel and they will be operating simultaneously. If you can see, one is clock and then one is clock bar. Okay, this, right? So suppose this is A and this is A bar. That means if we making it A equal to VDD, okay, then clock bar equal to 0. So PMOS will on also as well as NMOS will on to pass the information. If it is not on, means it will remain in the invalid high impedance state. Okay, so you can see it will pass the information only here also in pass transistor. It will pass the information only when the NMOS is connected to on, when NMOS should be on while passing the information. So here also it is connected in parallel. So any information is coming at this particular node, X will be equal to X here if this clock is working. Okay, so this will remove the use of basically CMOS. CMOS we required two inverters we required. So but here we can utilize only two transistor, okay, instead of a 4 transistor. Then we can get the same functionality, and there is no disadvantage as such like a pass transistor. So since we are using both the transistor NMOS as well as PMOS, so whatever inputs will come, whether the input is 0 or input is VDD, it will give the correct output. If input is 0, it will give the output as V0. If input is VDD, it will give the output as VDD. That's it. Okay, because both NMOS and PMOS are in parallel. Because if one information is there, like 0 information is there, NMOS is conducting, that means it will give a good 0. And if VDD is there, so NMOS, PMOS both are operating, so PMOS will be dominating and it will give the information as a 1 VDD. So that is why in case of a especially D-latch kind of implementation, we use transmission gate logic. Okay, otherwise if you go like with the conventional way, we have maybe come up with the increased number of transistors. Okay, so that is why for a multiplexer design or D-latch implementation, okay, so for that transmission gate switches are being used. Okay, and the TG is activated with clock while the latches feedback loop TG is activated through clock bar. So you can see now I'm going to explain about the D-latch transistor. Okay, D-latch logic. So how it will behave. So this is the equivalent CMOS implementation. Okay, so you can see that D will be passed to if the clock is arrived, it will pass information D here. Okay, and it is connected to inverter, so it will give the output Q bar. Okay, and then it will give the Q bar is again inverted, it will give Q. Okay, and then Q is like feedback. As you know that for any latch kind of information we require a feedback. Earlier SR latch, JK latch, in all those things we are also using the feedback. Okay, so so because your latch implementation is depends on the input as well as the previous output. Okay, so that is why previous output has been fed back to this particular point. Okay, so if this particular what is the functionality of D latch implementation is that it will shift the information in serial, right? So it will shift the information in serial. For that only we have utilized the transmission gate logic, because it will just pass the information from the one level to one inputs to another end by using the clock. Okay, if clock is working, it will pass the information. If clock is not working, it will not pass the information. So here, important thing here, when the transmission gate is activated, the clock is in the feedback loop. We have a clock bar. These and are not the similar one. So if D information is there, it will clock the information here, and at this particular time it will not be working. Okay, when the opposite clock will happen, then this information will be passed to this particular node. Okay, so you can see this D-latch implementation, how it will works basically. When clock is 1, this switch is on and this switch is off. Okay, when clock is 0, this switch is off, then this will make it on. Okay, so that is why if a clock is there, okay, and you know there is an important point, T setup time and T hold time is required. Okay, so that is why this particular things are being shown. For certain period of time, the input must be stable, and after some period of time, or input must be stable. That is called the setup and hold time. So accordingly, the information will be conveyed. The D information will be sent to Q based on the clock uses. Okay, so accordingly, you pass the information to D to Q by using the suitable value of clock time period. Okay, so this is the alternate is it, so that alternate way of implementing. If you don't want to use the transmission gate logic, then your implementation of a D latch will be something different, using only the CMOS logic. Okay, not the transmission gate logic. But preferably, if you want to reduce the number of transistors, okay, we go for a transmission gate logic. Okay, so these are the various circuitries are also there. Okay, D resistors, D flip flop, all those things. Okay, I am just going to share information with you. Okay, and it at least you go for a few simple circuits. Okay, and then you use the circuits, how it can be used for a CMOS implementation. In terms of that, you need to understand. So only whatever point I have covered about the SR latch or the up to D flip flop, you can use this CMOS circuit for implementation purpose. Okay. So no need to go in details part. Okay, only SR latch, JK latch, and D latch we have gone through in this slide. You can use for the reading purpose. Okay. So another important topic that is remaining is the memory. Okay, so today we do not have sufficient time, so I'll schedule the class on next week for that. So I'm going to start the attendance also. So please mark your attendance.
So please share the slides.
Yes, sure. I forgot actually yesterday, I need to share, but I'll definitely upload today. So whatever the different topics we have studied, I think I have uploaded this slide up to this layout and all, right? So I need to upload the slides related to combinational circuits and sequential circuits, right? So combinational circuits, including dynamic logic, domino logic, NORA logic, whatever we have discussed, and the sequential circuit, I'll upload timing diagrams and this particular site is we discussed today about the different circuits implementation using the CMOS. Acha, one is asking uh, quiz timing. Okay. So let us know when you are uh, when you can give the quiz.
So next Friday.
Next Friday. What about others?
Yes,
Because
sir. Next Friday.
26 will be the 26 there is a national holiday, right? My class in 26 and then 27 I have a class in 28. Okay. Okay, then I'll take a class and revise the things on 27 and then we'll take a quiz on 28. Okay.
Okay, sir.